Okay, let's hear if you came up with anything, or I don't know if you have something to share. If not, that's okay, but hopefully you've at least started thinking about it and talking about it, and you're sort of maybe even not sure, but you're wondering, that kind of thing. Does anybody have anything that they thought was interesting about what they talked about, or is it just straightforward? Yeah. Okay, so very good. Yep. What else? That's a really important idea, that the slope of the tangent. So I'm gonna sketch something, but I'm gonna erase it so I wouldn't copy this. If I have some graph, okay, it's increasing up to that point, and we notice the tangent has a positive slope all along there. So like that's what the relationship is. That if the slope of the tangent is positive, then the function is increasing. And then if the slope of the tangent is negative, the function's decreasing. And if the slope of the tangent is 0, then that's a turning point. That's what we talked about last week. And so if I look closely, zoom in at this turning point, right at the turning point, it is 0. Right before this turning point, the slope in this case is negative, and right after, the slope in this case is positive. And if I even draw that, right, let me do that again. If I get this one, then this one, then this one, it shows that the graph is turning inside like that. So it's got a minimum there, right? We call that a local minimum. And then if we put this curve back in like that, at that maximum, slope of the tangent is 0, and right before the slope is positive, and right after the slope is negative. So then that shows me that it's a maximum in that point. Okay, so that's really important to be visualizing that, thinking about that. But the other thing is, if we have, now that we can take derivatives and we can come up with a derivative function, okay? So if I have a derivative function, right, and we talked about this, I don't remember, quite a while ago, like it's a function itself and it has properties like any function has, right? And our understanding of those properties is really useful. So the properties of the derivative function will tell me a lot about the original function as well, and whether it's increasing or decreasing. Okay, so let's take a look at an example here. This is one that I think you'll want to sketch. So I'm just going to draw some axes, and it's just rough again. I'm going to go like this, something like that. Okay, so I'm going to say this is -3 just because we're going to talk about it. I guess this one will happen at 0. This will be at, well, let's say +4. Okay, so those are kind of interesting points where something interesting is happening. And here's what we're going to do. We're going to draw a little table over to the side here. So if I start thinking about the derivative of this function, I don't necessarily know exactly what it's going to look like, but I can start to sort of think about it. It would be from -3 and earlier, it's increasing. So that means the slope of the tangent is positive. So that means the derivative function would be positive at all those points. Okay? And then it's 0 at that point. So it's It's 0 there, and it's positive there. Then it's negative because it's decreasing, and it's going to be 0 there. Okay. Then it's increasing, so it's positive, and it's 0 here again, but it's still increasing after. Is that right? At when x is 4, it's increasing before and increasing after the function, the blue one. So the slope of the tangent is still going to be positive. Now that might be a little bit tricky, but you can trust me, that's about what the derivative function would look like. Okay? If I took the derivative of this, that's about what it would look like. And if we go back to MHF, the blue curve does look like it could very well be an odd degree function. Well, it is an odd degree function, and the derivative will be 1 degree fewer. It'll be even, right? And that makes sense. So it all kind of fits if we think about it. And we could use technology to kind of look at this maybe a bit more carefully, but I think this is good enough for now. So what it's telling me is if I can find if I have the derivative of a function, I can determine those critical points. We've already done that, where you might have like a maximum or a minimum, a turning point. And I can do some interval testing, and I kind of know that in between those important points, there's nothing interesting happening. But at in those critical values, there's something interesting might be happening. So we can test the intervals, and we can kind of figure out what's going on. So let's take a look at that. I think it'll make more sense once we get into this. Okay. So, and this is how we will typically set up our table. We have x, the derivative of x, or derivative of f and f. Usually we do it in that order. And we're doing this from the graph, just visualizing, but eventually we'll be doing it from algebra. Okay, you'll take the derivative of a function in order to be able to do this. So here's all of the intervals that I'm going to break this up into that are going to be where something interesting is happening, or that represents each interval. When x is less than -3. And the derivative is positive here. Is that correct? Okay. So that means the function is increasing. Then I'm leaving a bit of a space here on purpose. I've got from -3 less than x less than 0, and in between those is -3. I have to consider what's happening at that point. At -3, I know that the derivative is 0. After -3, I can see that the derivative is negative. So it's decreasing. I should have mentioned this before. Reminder of what increasing and decreasing are, because we talked about this in MHF and we've talked about it a bit in this course, but some people I know still have a little, or don't quite get it. So I'm going to examine the function up to this point, and as I'm going to the right, so as x's are going to the right, what are happening to the y's? They're getting bigger. And then at that point, what's happening to the y's? They're getting smaller. And then at that point, they're getting bigger. And then here, they're still getting bigger, right? So that's what we mean. X's are always going from left to right. That's the input. What's happening to the y's? Is the graph going up or is it going down? Moving from left to right. Okay, does that make sense? But we always talk about x values, the interval on which it is increasing. We don't care about how much is increasing or where it increases to. That's what some people think. They get stuck on that point, that it's increasing to that point. That's not what we usually care about. We care about, like you might care about what that point is for a different reason, but when we're talking about intervals of increase, it's always x. Okay. If anybody's unclear on that, make sure you ask, because that's super important. So then I look at this table and I see that it was increasing before and is decreasing after. So I can conclude that's like the idea that it was increasing, it's 0, and then it's decreasing. So that must be a local max and like a turning point. And I might eventually I'll know what that point is, and that'll be useful, but because this is just a sketch and we don't actually have a function, we don't. So that's fine for now. Okay, so now we're going to look at 0. And at 0, again, our derivative is 0. And between 0 and 4, our derivative, I'm looking at the green curve here, but I'm also looking at the blue curve. Like I can see that the blue curve is increasing. So if I can see the blue curve is increasing, that tells me the derivative is positive. If I can see that the derivative is positive, that tells me that the function is increasing. Does that make sense? So the function, the derivative is positive, so it is increasing. And again, I can do the conclusion that it was decreasing before, and then it's 0, and it's increasing after. So that has to be a local minimum. Okay, and the last one, something different happens here. And I'd be curious if when you were chatting at the beginning of class, if you kind of thought about this, and maybe not, but this is what I was hoping that people would try to think about, all the different things that might happen. So at 4, the derivative is 0, which when we were doing max optimization and max min problems, we saw that those were where the derivative was 0 or where it did not exist. Those were the places where you might have an optimal value, right? And those are the ones we would explore and we'd test them. It's been a week now since we've done this, so maybe we got to remind ourselves exactly what we were doing. But then after 4, so when x is greater than 4, I see that it's increasing again. And I see that the derivative is still positive. So what happened there? Well, it's not a local max, not a local min. It's like a twist, or it's neither. Whoops, if I can spell neither. Okay, and so we, again, know what the function looks like because we visualize that it's increasing before, then it's 0, and it's increasing after. Does that make sense? We also notice that this is polynomial, so x, like the function exists everywhere. We can see that if it didn't, then we'd have to look at something. But for the next couple of days, we're only really looking at polynomials, so we don't have to worry too much about that. Is it making some sense? What do you think? Any questions? So we're not going to do this whole process again, but what might a graph do that's related to increasing and decreasing but looks different from the sort of what we saw here? In a polynomial, that's kind of all you get. You get turning points, or you get intervals where nothing is changing, or maybe you get a twist. You don't really get anything else with a polynomial graph, right? So that's kind of sums up what a polynomial, the different options that you might have for a polynomial in that table. So what else might happen?
What if you have a hole?
So if you had a hole, it wouldn't be a polynomial. It'd be some other kind of function. And absolutely in that case, you would have to examine what's happening at that point in the graph, for sure. Yep. So if you have a hole, that would be another one. What else? Yeah, good. So if we have some kind of, one of those piecewise functions that have all kinds of, so I could have my graph coming down like this, and then, so that's decreasing, and then increasing. Very good. So what would be happening there? The derivative wouldn't exist, right? And so we would check, I guess, what's happening there. That might be a tricky one. Anybody think of another situation? Very good, asymptotes. So asymptotes could look a couple of ways I can think of. Might go like this. Oops. So it might be like, let's see what's happening here. This is increasing, still increasing, and then decreasing. So at an asymptote, it changes. And you don't have a local max or a local min because it's an asymptote, but something's happening there. Very good. So that's one of the other sort of situations you might have. Or the other one that I can think of is, it's more or less the same, but if I do like this, I mean, maybe it looks like, I don't know. You remember what these graphs can all look different. And so where we're going with this, and we're not doing it yet, but we'll start doing a little bit tomorrow. Where we're going with this is curve sketching. So we could sketch curves with certain amount of accuracy in MHF. There were things that we could do, like we could find all the x-intercepts, we could find the y-intercept, we could find asymptotes and detect the behavior around asymptotes so we could get a general idea. But we couldn't do things like find that kind of a turning point or that kind of a turning point. And when we sketched polynomials, I could sketch polynomials where they had their x-intercepts were like turning points, right? Where it could be factored. But what about a polynomial that's not factorable? So I have turning points that are not on the x-axis. How do I find those? We couldn't find those before. Now we're going to be able to. Okay? So that's where this is going. But for today, we're just really starting to explore the idea of increasing and decreasing and how that helps us visualize the graph. Does that make sense? All right, so we're going to do one example, and then that'll actually be it, I think. Any questions about that so far? So suppose the derivative of the function f is f prime, and it's given to us, and it's given to us in factored form, which is useful. We want to determine the intervals of increase and decrease of f. So we're going to do this by building the same table that we built on the last page, but I'm also going to scribble some other things just to help illustrate what I'm thinking. Okay, but the table is like the product that we want to show. Okay, that's what we're going to get. So the other stuff that I add in, I'll do it in a different color, and it's not necessary. And this is where, when I go back to MHF and I think of, so for example, like I'm just going to scribble something here. When f prime of x is greater than 0 or less than 0, which means this, it's like an inequality, right, that we did in MHF. And we know how to solve these. See, everything we do it for a reason. We explored these skills, polynomial inequalities, because now we need to be able to do them. And we know that we want it to be in factored form, and we want the right side to be 0, so greater than or less than 0. And that's when the derivative is positive or negative, when it's greater than 0 or less than 0. And that tells me that the original function is increasing or decreasing. Does that make sense? So I'm thinking of a number line here. I'm visualizing this as a number line. And my intervals of interest, where the x-intercepts of the derivative. Again, if I go back to this original graph, okay, when I have an x-intercept of the derivative, I've got a turning point. That's where the original function has a slope of 0. Something's going on. So that's why we care about the x-intercepts of the derivative. Does that make sense? So the x-intercepts of the derivative are -5, -1, and +3. Okay, and I'm just visualizing these as my intervals that I'm going to check what's happening in each interval. So like I'm going to check in here and in here and in here and in here and use that to deduce what's happening at -5, -1, and 3 as well. Okay? And I'm going to pick a random number to represent that interval, and I'm going to check to see if it's positive or negative in there. And there are other ways that you could do it. If we know enough about this function, I know that it's cubic, and I know what polynomial is. So you can use other things to make sure that you are getting it right. But it's not always going to be that easy. Sometimes we're going to have to test. All right, so here we go. We're going to start building our table. X, f prime of x, and f of x. And whoops, what's going on here? F prime, I'm just going to write in the function because I can't see it, equals x plus 5, x plus 1, x minus 3. Something like that. Okay, so we're going to check here, x less than -5. And I'm just going to pick, and again, you don't have to say what value you're using, but I'm saying it and I'm writing it down so that what's happening in my head, you see what's happening. So I'm just going to use -10 to represent, and I just picked that because 10's an easy number and it's big enough that it's going to kind of work, and using a big enough number that makes the math trivial can be a good idea. So when I plug -10 into the derivative, okay, I get -10 plus 5, so that's negative. -10 plus 1 is still negative. I don't care exactly what it is. I care that it's positive or negative. And I get -10 minus 3 is negative. So I get 3 negatives multiplied together. So my result is negative, which means the original function is decreasing. Do we all get how this works? At -5, I know that it's 0. And then from -5, less than x, less than -1. So pick some value. I'll use -2. So I'm going to use -2. Make sure it's in that interval. Don't allow that to be your mistake. I could imagine if there were fractions, like I've seen people make mistakes, that kind of thing. All right, so -2 plus 5, that's positive. -2 plus 1 is negative, and -2 minus 3 is negative, so I get 2 negatives, so that works out to be positive. So now it's increasing, and again, that means if it's decreasing before and then increasing after, it's going to be a local min. And I would, you could draw it. Draw yourself a little sketch. Wait a minute. It's decreasing, and then it's 0, and then it's increasing. So the function must be going in there. And again, this may seem simple, but I think it can be confusing because we're flipping back and forth thinking about the derivative. Where is it positive or negative? What does that tell us about the original function? What are we drawing conclusions on? Does that make sense? Which one of these things is which, right? Like the derivative is cubic, but the original function is not. So we got to make sure we always keep those clear. Okay, let's finish this off. At -1, it's 0. From -1, less than x, less than 3. So I'll pick 0. Whenever I can use 0, then I like to. It makes math easy usually. And be careful, don't use 0 if you can't use the numbers that are at the edge of the interval. So we can't use -1, we can't use -5, right? So don't use those. If 0 was one of those, then we wouldn't be able to use it. So 0 plus 5, I get positive, positive, negative. I get 1 negative and 2 positive, so it's negative. So it's decreasing. Decreasing. And then what happens at 3? And then when x is greater than 3, so I'll pick some big number, 10. So I get positive, positive, and 10 minus 3 is still positive. So all of those are positive. So this is increasing here. And it's 0 here. And so I can fill in the gaps. Again, it was increasing, and then it was 0, and it was decreasing. So this is a local max. And then it was decreasing, and then, so this is a local min. Does that make sense? Any questions? Determine the intervals of increase and decrease. Like, that's it. It's summarized in that table down that far right column. Oh, here, I'll fill in these. I used 0 for this one, and I used 10 for this one. Mason. Yeah, I mean, it's sort of similar. So in math, we differentiate between a global maximum or minimum and a local maximum or minimum. So this graph does, it's decreasing, and then it's increasing, and it's decreasing, and then it's increasing. Does something like that. So it has, this is a local max. It's not an overall max. This function has no overall max because it goes up forever. It will have an overall min. It's going to be one of those two. I don't know which. The other one will just be a local minimum. So the word local, in this case, whether you use it or not, I'm not actually going to be all that concerned about that. But it's the difference between a local, it's only minimum compared to other areas really close to it. Whereas sometimes we might be interested in the overall maximum of the entire function, which we call a global maximum. And then you call them global variables as well because they're accessible everywhere, or local variable because it's only accessible to the function or depending on what you're doing, right? So, I mean, kind of similar, but yeah. Other questions? Okay, there's your practice. There's a few. Some of it's quite straightforward, just thinking about increase and decrease, looking at graphs. There's a couple of questions, I think, where you use a table like that, and there's a couple that will kind of make you think. There's a couple of questions that give you some clues, and you have to use those clues to try to draw the graph. I cannot stress enough how important I think those questions are. Don't skip them. Think, oh, this is making my brain hurt. It's making me actually think, and it's Monday, and I've just had a week off. I can't think right now. Don't do that. Make yourself do it. Do the thinking. I think those are really good questions that will really help with what's coming next.